Hi, this video will discuss the procedure and computation of Fieldwork 8 in Fundamentals of Surveying, determination of the height of a remote point. This fieldwork will show how points of interest with a tall height can be measured by the use of a proper understanding of geometry and a theodolite. This knowledge is important for a surveyor since it is not uncommon for points with high vertical distances to be inaccessible, as well as illogical to be measured using a more brute force method, such as using a tape measure.
The instruments that we use in this fieldwork will be a stick as an improvise for a leveling rod, marking pins, a tape measure, and a theodolite. This will be the first time that a theodolite will be needed for fieldwork. Theodolite is needed in this fieldwork since the vertical angle from the horizontal level is needed.
For the procedure of the fieldwork, the chief of the party first designates which point of interest the surveyors will be observing. The instrument man will then set up the theodolite on a suitable spot where the topmost part of the point of interest can be seen. Label this spot as Station A. In this fieldwork, the point of interest will be the top of a mountain. In setting up the theodolite, the instrument man first levels the theodolite parallel to the horizon. Then, a rodman will then set and hold a leveling rod vertically near the base of the point of interest in order for us to read and measure. After that, the instrument man then spots the peak of the point of interest accurately while using the micrometer scale. This angle will be denoted as angle alpha normal. Therefore, the value that we obtain here is 35 degrees 52 minutes. Furthermore, the instrument man then levels the theodolite and sights the reading of the leveling rod in order to get the height of the instrument. For our vertical height, in the case of normal reading, we get the value of 1.45.
Next, the instrument man then rotates the telescope about the vertical axis by about 180 degrees, essentially using the other side of the telescope to spot the point of interest. This angle is then denoted as angle alpha inverted. A rodman will then hold a leveling rod near the base of the point of interest in order for us to measure these angles, and are then recorded into the surveying notes by the recorder. The process of inverting the telescope is done to determine the index error of the instrument. The mean of the normal and inverted angle alpha is then computed. Therefore, the value that we obtain here is 35 degrees 45 minutes. Then we will now measure the vertical height of the instrument in inverted reading, in which the value that we get is 1.43. The mean between the two angles will be used as the angle alpha in the computation later on. The instrument man then moves the instrument a certain distance towards the point of interest, calling it Station B. The instrument man must ensure that the point of interest and the leveling rod at the base of the point of interest are both visible.
After the instrument man sets the station B, the instrument man then sights the top of the point of interest. The normal and inverted reading of the angle beta is then recorded. The mean between the two angles will be used as the angle beta in the computation later on. The angle beta for normal reading has the value of 37 degrees. Then, we will now get the vertical height of the instrument in the normal reading. As you can see, we obtained the value of 1.17. For the inverted reading, we will do the same procedure from station A. Now, the value that we obtain for angle beta in inverted reading is 37 degrees and 10 minutes. Then the instrument man then levels the instrument once again and sights the leveling rod. Next, the reading that will be obtained for the leveling rod will be the height of the instrument for station B. We will now be measuring the height of the instrument from the inverted reading and obtain the height of 1.20. After that, The distance between station A and station B is then measured using a tape measure by two tape men. The distance is then recorded by the recorder. After recording all the observed data, we can now analyze the data with the use of geometry in order to solve for the height of point of interest.
Work number 8. Determination of the height of a remote point. So for the computation of the height of the remote point, first we have to determine the difference elevation between the two instrument setups. And the formula to be used is the difference in height is equal to h sub 1 minus h sub 2. Second is analyze triangle BEF, solve for the distance x using tangent function. And the formula is tan beta is equal to x all over the difference in height. The third is determine the sum of the distance AB and x for the analysis of the oblique triangle. The formula is the distance of AF is equal to AB plus x. So the fourth step is using the sine law in the oblique triangle AFD, solve for the distance FD. So the formula is AB plus x all over sine times beta minus alpha is equal to FD all over sine A. And the fifth and final step is using the right triangle FDG, solve for the height of the remote point BG. And the formula is sine beta is equal to h minus h sub 1 all over FD. So here is the instrument setup used to conduct this field work.
We have the following given data: angle A and angle B, the height of instrument A and the height of instrument B, as well as the distance AB being 4.75 meters. To find the mean angle, it is very simple. We simply need to add the two given or recorded data and divide them by 2. So for A, it would be 35 degrees, 48 minutes, 30 seconds. And for angle beta, it would be 37 degrees, 5 minutes. And the same will be done to find the mean height of the instrument. 1.45 plus 1.43 all divided by 2 would be 1.44 meters. And 1.17 plus 1.20 divided by 2 is 1.185 meters. Now to find the computed height of remote point, we must first use the formula tan beta is equal to the height of instrument A minus height of instrument B all over x. Now, substituting the data that we have, in order to find x, it would represent 1.44 minus 1.185 over tangent of 37 degrees and 5 minutes. So x will be equal to 0.337. And to solve for distance of AC, it will be equal to distance of AB plus x. So that would be 4.75 plus the computed value of x, which is 0.337, in order to find distance AC, which is equal to 5.087. Now to find theta, in this scenario, it would be beta minus alpha. So 37 degrees, 5 minutes, minus 35 degrees, 48 minutes, and 30 seconds. So the value of theta is 1 degree, 16 minutes, and 30 seconds. And to find the distance of CD, we will need to use the sine law, which is the distance of CD over sine of alpha is equal to the distance of AC over the sine of theta. Once computed, we will have the value of distance CD, which is 133.759. And to find the computed height of the remote point, it will be equal to the formula. The sine of beta is equal to the computed height of remote point minus the height of instrument A all over distance CD. And transposing in order to find the formula for the computed height of the remote point, which would lead to the result being 82.093 meters. And here is the sketch used in Fieldwork 8. As you can see, here is the mountaintop, here is the rod used, and this is B and A. That is all. Thank you.